Mastering supervised learning. Machine learning's dirty secret: not all learning is created equal. Where can one find the key distinctions between supervised learning, which involves training a model on labeled data to make predictions, and unsupervised learning, which focuses on identifying patterns in unlabeled data, as well as reinforcement learning, which involves an agent learning through trial and error, and how do these differences impact the performance of each approach in real-world applications? The key distinctions between supervised learning, unsupervised learning, and reinforcement learning lie in their underlying objectives, data requirements, and learning mechanisms. Understanding these differences is crucial to selecting the most suitable approach for a particular problem and achieving optimal performance in real-world applications. Supervised learning. In supervised learning, the primary objective is to train a model to make predictions on new, unseen data based on labeled examples. The model learns to map inputs to outputs by minimizing the difference between predicted and actual outputs. The availability of labeled data, where each example is paired with a target or response variable, is the hallmark of supervised learning. This approach is further divided into two subcategories: regression and classification. In regression, the goal is to predict a continuous output variable, such as stock prices or temperatures. In classification, the objective is to predict a categorical output variable, such as spam versus non-spam emails or product categories. Supervised learning has several advantages, including high accuracy and reliability, especially when the labeled data is abundant and of high quality. Ability to learn complex relationships between inputs and outputs. However, supervised learning also has some limitations, such as required large amounts of labeled data, which can be time-consuming and costly to obtain. Relying heavily on the quality of the labeled data, which can lead to biased or inaccurate models if the data is flawed. Unsupervised learning. Unsupervised learning, on the other hand, involves identifying patterns, relationships, or structure in unlabeled data. The goal is to discover hidden insights or groupings in the data, such as customer segmentation or anomaly detection. Since no target or response variable is provided, the algorithm must find meaningful representations or clusters in the data. Unsupervised learning is particularly useful in exploratory data analysis, where the goal is to understand the underlying structure of the data. Identifying novel or unexpected patterns in the data. However, unsupervised learning also has some limitations, such as lacking clear evaluation metrics, making it challenging to assess the performance of the model. Requiring careful feature engineering and pre-processing to ensure the algorithm can identify meaningful patterns. Reinforcement learning. Reinforcement learning combines elements of supervised and unsupervised learning. The primary objective is to train an agent to take actions in an environment to maximize a reward signal. The agent learns through trial and error by interacting with the environment and receiving feedback in the form of rewards or penalties. Reinforcement learning is particularly useful in robotics and control systems, where the agent must adapt to changing environments. Game playing, such as chess or Go, where the agent must learn to make optimal decisions. However, reinforcement learning also has some limitations, such as requiring a large number of interactions with the environment to learn effective policies. Suffering from the curse of dimensionality, which makes it challenging to explore and learn from high-dimensional state and action spaces. Impact on real-world applications. The choice of learning approach significantly impacts the performance of a model in real-world applications. For instance, in image classification tasks, supervised learning has led to remarkable breakthroughs, enabling applications like self-driving cars and medical image analysis. In recommender systems, unsupervised learning can help identify user clusters and preferences, leading to more accurate personalized recommendations. In robotics and game playing, reinforcement learning has enabled agents to learn complex behaviors and achieve superhuman performance. In conclusion, understanding the key distinctions between supervised learning, unsupervised learning, and reinforcement learning is crucial for selecting the most suitable approach for a particular problem and achieving optimal performance in real-world applications. By recognizing the strengths and limitations of each approach, practitioners can develop more effective models and drive innovation in various fields.